It's a great pleasure to be here. I'm delighted to see you all here. I have to confess, when Glenn asked me to do this with him, I think we both enormously underestimated the task of taking 5 or 6 decades of work by thousands and thousands of people and compressing it down into 3 hours without the use of equations. In any case, what I want to talk about tonight, as Glenn indicated, was the standard model of particle physics, and in particular talking about fundamental forces, and culminating in our understanding of the origin of all mass. So it's heady stuff. So the talk is in 3 parts. First is terms that you will learn along the way: fundamental forces and gauge bosons. Then the second act will be to answer the question, how do we know? And then the third will be to tackle the question of how we understand mass is generated, and to sort of advertise that we are on the verge of knowing whether or not this is right. So what I want to start off with is actually reviewing where Glenn left off last time. Then we'll talk about interactions between those, and then some mixing and matching of it. So last time Glenn told you that basically all matter that we know, we first realized was made out of atoms, then that the atoms are composed of electrons, negatively charged particles circling around a much, much smaller nucleus. The nucleus held together by a force called the strong force, composed of protons and neutrons, and that those protons and neutrons in turn were made out of quarks and antiquarks, specifically up quarks and down quarks. So almost everything that we know of, that we see that we're made of, is in this first column. Up and down quarks making up protons and neutrons, and the electrons orbiting them. However, as in the course of the 30s and 40s and so on, as physicists began to explore the world further, additional particles were discovered. First was the muon, which looks like a heavy copy of the electron. It's about 200 times as heavy. When it was first discovered, Wolfgang Pauli, the famous physicist's response was, "Who ordered that?" This was basically repeated over and over again. After the up and down quark, I think Glenn told you about the strange quark. Then subsequently in the early 70s, the charm quark was discovered, and then quarks called top and bottom. Physicists, as you may have gathered, tend to use somewhat facetious naming schemes, not always very imaginative. Now, Glenn also told you, I think, that the electrons are held in orbit around the nucleus by the electric force, which we've understood since Einstein in the early days of the 20th century is carried by particles called photons, light quanta. And then what he probably only vaguely alluded to, I think, was that the strong force is carried by particles that look like 8 copies of the photon in first approximation, also have no mass. And then the weak force, responsible for decay of nuclei in radioactivity, is now understood to be carried by sort of things that look similar to the photon but weigh about as much as a rubidium atom. And so the question is how to make sense of all this. Now, one thing that I did want to call your attention to is the neutrino. Has a close connection with Case Western Reserve history. Fred Reines, who won the 1995 Nobel Prize for the detection of the neutrino, this very lightweight particle with no charge that interacts only exceedingly weakly, was in fact chair of the Case Physics Department from 1959 to 1966. Now, in actually working out this theory, there's a formidable amount of mathematical heavy lifting that has to be done. And in the 1930s, as the theory was being developed, the computations that were developed were just long, tedious, and prone to errors. In the late 40s, then young physicist Richard Feynman came along and realized that you could compress all that mathematics into a series of pictures. And the pictures basically could be reduced to a couple of things. You have lines with arrows on them that represent mathematical expressions covering electrons or things similar to electrons, and squiggly lines representing photons or things similar to that. And they can interact basically at a point, and so they bounce off. Now, this represents a very well-defined mathematical equation. I'm not going to write it down. We don't need that for what we're doing. What I want to do is point out some of the qualitative pictures that you can get from it, which will be important for what we're doing today. But every picture that I draw represents a very precise mathematical formula. So if we introduce the notion of time and ask what does that particular symbol represent? Well, it can represent several things depending on the ordering. You can have an electron coming along that a quanta of light, say this, bounces off an electron in the room. You would represent that process by a diagram like this. The electron gets hit with a photon, and the electron goes off in another direction because it's been hit. And so this is sort of a way of understanding the electric and magnetic force. You can also have a situation in which the electron is going along and it emits a photon, and the electron recoils in another direction. But you can also do things like this. You have an electron going forward in time, emitting a photon, and scattering backwards in time. And Feynman basically recognized that you could think of an electron going backwards in time as an anti-electron or a positron, which I think Glenn at least briefly alluded to, going forward in time. So what this represents is an electron going forward in time colliding with a positron moving forward in time and emitting a photon. So it's, this is matter-antimatter annihilation. And you can have the inverse process, in which you have a photon coming along and then designing to turn into an electron and a positron. And where, again, in some sense, you can think of the positron as an electron moving backwards in time. But all of these different processes are represented by that same initial diagram that I drew. So how would you actually know if this makes any sense at all? Well, so how do we measure it? First thing is how do you tell the charge of a particle that's moving along? Well, there's basically two things you can do. You can send a charged particle through an electric field, in which case, you know from combing your hair in the winter and so on, that static electricity will attract other charged things. So you can bend things that way. You can also, if you've got a magnetic field and send a charged particle through it, it will also bend. And so for a given magnetic field, a positive particle will move in one direction and a negative particle will move in the other direction. But how do you see the particles at all? Well, in early technology, originally was with what were called cloud chambers. The next generation technology were called bubble chambers. And what you see here is a famous bubble chamber called the Big European Bubble Chamber, because it was big and in Europe. For size, you can see my son here standing underneath. So this was one which was commissioned in the late 1960s. It was filled with liquid hydrogen. It had a big plunger. They dumped some particles through it, pulled the plunger down just before that, and when the particles went through, they would cause the hydrogen to boil along the trajectory, everywhere that the charged particles ionized it. So, and then they'd take a picture of it. And during the history of this, I think this chamber was used for something like 23 million photographs in 22 experiments over about a 20-year lifetime. And then someone had to go in and scan every single one of those photographs. Again, I point out the CWRU connection. The bubble chamber was invented by Don Glaser, who was a CIT class of 46 and won the Nobel Prize for this in 1960. So here is a nice bubble chamber photograph, and where what I want to call attention to, this curve coming along here is a positron, and you see it disappears right there. It's hit an electron in orbiting one of the hydrogen atoms, and so you don't see anything, but there's a photon, a gamma ray, that comes across. And then about here, that interacts and creates an electron-positron pair. And so you see the positron turning around this way and the electron coming around this way. And so what you see in that part of this photograph is both an antiparticle, piece of antimatter annihilating, and then the creation of antimatter together with ordinary matter here. And so before your eyes, these processes that we just talked about being played out. And so again, in terms of the diagrams, what happened is you had an electron colliding, a positron colliding with an electron, giving rise to a gamma ray, and then a new electron-positron pair being created. And basically, almost everything I do in this talk is going to be variations on this theme. So if we go back to the standard model, we were looking basically at interactions of this with this, but you could equally well work with muons, so that you could collide an electron with a positron to make a photon that would create a muon-anti-muon pair, and we'd see examples of that. You could, since it's also neutral, rather than have the photon, you could have the Z boson as an intermediate state, and we'll see how that's used to discover it a little later on in the talk. Rather than it being an electron or a muon or something like that, you could create a quark-antiquark pair. And we'll talk about examples of that and see pictures of that later on in the talk as well. And indeed, if you don't want to collide for technical reasons, sometimes it's easier, rather than colliding electrons with positrons, it's easier to collide protons with antiprotons. And since the protons are made of quarks and the antiprotons are made of antiquarks, what you're really doing is colliding quarks with antiquarks. You can again have the same intermediate process, and then that can fall apart into electrons and positrons, or muons, or more quarks or antiquarks, or just generically stuff and anti-stuff. And so we will see examples of all that as we go forward. Actually, this is a really convenient point to call it quits for this stage. The basic idea is again, that we've got simple diagrams that represent complicated mathematics, but the underlying processes are easy to visualize, and it's not abstract stuff. We can actually see it happening. And so we're going to use this over and over again to explore what the world is made out of at the very, very smallest distances.
I would have to assume that this is the same no matter where it is. It's not what we can see just on Earth, but that it would be the same anywhere in the universe.
The answer is yes. We believe, and in many areas can check, that the laws of physics are essentially the same. We know that the laws of atomic physics work the same everywhere. It's basically, we wouldn't understand the large-scale structure of the universe if that wasn't basically true. So now the one caveat is in the very, very early universe, and this will be something that you can come back and ask the question again after the third part. In the very, very early universe, when the universe was very, very hot, for reasons that I'll allude to later, or at least set up for you to ask the question again, the laws of physics could be somewhat different, and we'll talk about that, but only in a very well understood way.
So the quarks, are they detectable or observable anywhere, like in a collider? I hear they got this forces. If you send them apart, the binding force increases.
So Glenn told you that protons and neutrons, other particles, pions, I think he showed you a table which probably your eyes rolled up into the back of your head when you saw the hundreds of strongly interacting particles. All are believed to be made of quarks and/or antiquarks. But we've never seen a free quark or a free antiquark, and we don't actually expect to. And the reason is while I said the gluons are very similar to photons, there's a key difference. They interact with each other. And it turns out that because they interact with each other, if you imagine having a quark and an antiquark that you could hold on to and try pulling them apart, the force, if you do that with an electron and a proton, the force eventually falls off as you pull it apart. It doesn't fall off with quarks and antiquarks. And so instead, I brought along my handy prop. It's like a rubber band. And so, in fact, the origin of the string theory was rooted in just this, something we'll talk about next week. So imagine you've got a quark at this end and an antiquark at this end. You pull it apart, and as you know from pulling a rubber band, the force doesn't drop. But if you pull hard enough, what happens is it becomes energetically favorable to pop a new quark-antiquark pair out of the vacuum, so that this quark is now connected to a new antiquark, and this antiquark is now paired to a new quark. And what you've done is taken what was one meson and created two mesons. And so when you smash a proton into a proton, the quarks will interact, some of them will go out. And then you have these forces between them that sequentially split them into more and more particles. So when you try smashing a quark out of a proton or something like that, what you end up getting is a jet of particles strongly interacting. And this will be key in terms of what we talk about in terms of particle detectors and how you see them. But at the fundamental level, any time that you smash a quark out of a proton or anything of that sort, what you expect to see in your detector is a jet of particles going off in the direction that the quark was originally heading. Part 2. So we had the nice, the sort of the late 20th, early 21st century periodic table of fundamental particles that I just showed. How actually have we deduced that? Glenn told you sort of how we figured out the electron and some of the quarks, but how do we figure out the rest? So there's 3 parts to it, the story in terms of how we understand this experimentally. So one is I have to tell you a little bit about particle accelerators. Second, I have to tell you a little bit about particle detectors, because we've advanced far beyond the bubble chamber days. And then I'm going to show you a series of events that again, basically illustrate the kinds of things that I've just been talking about. So the world's premier particle accelerator these days is the Large Hadron Collider, which is located just outside Geneva, Switzerland. This is the yellow shows the tunnel. It's about, on average, about 300 feet underground. For scale, you see the Geneva airport here. This is Lake Geneva, Lake Leman here. These are the Jura Mountains in the foreground here, and Mont Blanc in the distance. It's 17 miles in circumference, and uses, when it's operating, about as much power as the entire canton of Geneva does when it's not operating. And the border between Switzerland and France runs along here, so the particles, travel internationally with great frequency. One of the things that's noted here is there's a couple of locations around the ring. Here, underground are large caverns dug out where the detectors that I'll show you a little bit about are located. The other thing I'd point out is in its current operation, there are 2 sets of magnets around here because it collides protons on protons. And so you need separate beams because protons are the same charge. The ring was originally dug in the 1980s, late 1980s, for an electron-positron collider. And so some of the results I'll show were from that phase where they were colliding electrons on positrons. Then to go to higher energies, they installed much more powerful superconducting magnets, and now we're colliding protons on protons. Now, just to show you, the yellow was this big ring here, and you see the locations for the 2 big detectors, Atlas and CMS. You can't directly send protons into that. You need to sort of accelerate it in stages to get it up there. And so there's a series of smaller accelerators. This one, the SPS, Super Proton Synchrotron, was built in the 1970s, and at that time was the highest energy accelerator. Now it's just used as an injector into the larger one. But we'll see some results from this. This also was the first accelerator. It was originally just protons, and then in the early 1980s, they developed techniques to store large quantities of antiprotons. And so they had protons going one direction around the ring and antiprotons going around the other direction in the ring, and studied proton-antiproton collisions. And then there's a series of smaller accelerators that basically raise the energy of the beam up to be able to inject it into that. It's a big operation. So this is what it looks like down in the tunnel. I'm actually a member of the smallest of the collaborations at the Large Hadron Collider called TOTEM, and I won't say very much about it. The main thing is you can see how big the tunnel is, and also note the bicycles here. Much of it is wide enough that you can get a cart through, but there's several sections where there's a bypass for the carts, and the only way to go great distances is actually to ride bicycles. And then this is actually the reason I was down there. You can't see that as well as I'd like. We've got a series of detectors, basically silicon detectors, that we move to within about 1 millimeter of the beam so that we can look at very, very small scattering angles and as I said, measure the size of the proton. And it turns out the size of the proton depends on the energy at which you measure it with. And so it's a number that actually is needed so that you understand how to calibrate everything else the machine does. Now, our experiment is on either side of one of the large detectors called CMS for compact muon solenoid, and we'll see more about this. This is just me setting the scale for the central part of the detector there that you see in the background. And here's, from a slightly different viewpoint, a sort of a fisheye view to see that, so you can see that what you could see in the last photo was only a small portion of this entire detector. And again, you see the person down here to set the scale. So this is big. I should mention it's not only physically big. It's a collaboration of about 2,500 PhD physicists at about 180 institutes and universities in 38 countries. Planning for it started in 1988, I think, and effectively it only started to operate about 2 years ago. So it's a major, major enterprise. So what's actually going on? So this is sort of the proton beams come into or out of and collide in the center of this detector here. And what you're seeing in this section is sort of a cross-sectional area of this octant. So there's a series of detectors. In the inner 3 feet or so are a series of planes of silicon that are very thin. So when a charged particle goes through, it records what the location of that charged particle is going through. And because you have a series of them, you can basically piece together the tracks of individual particles. Then you've got a layer which is about 3 feet thick of lead. And when an electron or a gamma ray hits the lead, it causes a shower of electrons. It interacts electromagnetically, and you just get this big shower of electrons, which is contained within it. And if you drill holes in the lead and put in glass fibers that have been doped with suitable chemicals, when one of those electrons hits the fiber, it gives off a pulse of light. And if you collect all the light, the intensity of that pulse of light is proportional to the energy of the particle that hit it. And so that's called a calorimeter, but it's basically a way of measuring how much energy that particle deposited. Now, behind that is about another 10 feet of, I think, depleted uranium in this case, but again, very heavy. If you have a strongly interacting particle, like a proton or a neutron or a pion, it'll be stopped in here and will also cause showering. You again drill holes in, put in fibers or something like that, collect the light, and that gives you a measurement of the energy of that particle. Then, since they wanted to directly measure the energy of charged particles magnetically, there's then a giant, at about 10 to 12 feet out, there's a giant superconducting solenoid to create a magnetic field within this whole thing. So this is just an enormously intense, huge magnetic field with an enormous amount of energy stored. Now, if you remember sort of the field lines on the Earth or something like that, magnetic field lines like to go out and then they have to go somewhere and come back again. And since you don't want these strong stray fields, you want to know where they're going. They then have a series of iron return yokes that have the field coming back through them. But in between them, they place more chambers to track charged particles. And the way this can be used is as follows. If you see a charge track going through the inner chamber and depositing energy in the electromagnetic calorimeter, you know that's an electron. If you don't see any charge tracks, but you see energy in the electromagnetic calorimeter, you know that's a photon. If you see a charge track depositing energy in the hadron calorimeter, you know that's a proton or maybe a charged pion, something like that. If you see no tracks in the inner part and energy in the hadron calorimeter, you know that's a neutron or some other neutral hadron. And if you see a charge track in the interior, no energy deposited there, but see the tracks out here again, that's a muon. So depending on what you see where, you know what the particle is that you're observing, and you've got multiple measurements of what the energy of it is. And the reason for the size of the whole thing is the laws of physics say if you want to stop the hadrons, you need 10 feet of lead or uranium surrounding everything. Then you've got to have your magnet. Then you've got to have your return yoke. So this whole thing is, about 7 meters in diameter, so about 25 feet halfway. So the whole thing's the size of a 5-story building.
7 meter radius.
7 meter radius, yes. Yes, so that's why. Now, so how does this work? This actually is going back to a much earlier experiment at the SPS. This is in 1983. This was an experiment called UA1. There was a proton beam coming in here, anti-proton beam coming in here. It collided. And what you see coming out here is charge tracks in the inner part. This is their way of displaying that energy was deposited in the electromagnetic calorimeter. And then the dotted lines here just show you where it would have gone. And you don't see any energy deposited further out. So this is an electron. This is an electron. And the energies of those two electrons sum up to the mass of a Z boson. And the rest of this, remember when you're colliding a proton and an antiproton, you're colliding a quark on an antiquark. Well, something has to happen to the other quarks and antiquarks in that. They basically just go in the forward direction through that process of rubber band splitting that I talked about. And so these are completely uninteresting tracks here. But what this is actually the picture of the first Z boson that was ever seen. And so it was kind of cool. When it first appeared, right, everyone got terribly excited because this had been predicted for well over a decade. And then actually to build a machine, turn it on, and see it right where it was expected to be was quite amazing. Now, you want to have lots of cross checks. One of them is if the Z is doing what you expect it to, in addition to turning into electrons, it should turn into muons. And so this doesn't show up as well as I'd like, but this is the same detector. Proton coming in, antiproton coming in. You see the remnants of the two. And then what you see here is a charge track, no energy deposited in the calorimeters. And then out here in the muon chambers, you see tracks again. And the same thing with this one going in this direction. So this is a muon, and the energies of the two add up to the mass of the Z boson. So this is the creation of a Z boson decaying into a muon and an anti-muon. Now, just one event, there's any variety of things that could fake it. What you really need to do is a large number of them. So when they built the electron-positron collider, what they could do was change the energy of the beams and slowly ramp it up, run it one energy one day and then take it to a higher energy. You sit at one energy, you count how many Z's do you see. And this is essentially what's being plotted here. At 88, you saw 5 in some unit time interval. 89, you saw 7 or so. You ramp it up to, what's that, about 87 or so. You see about 17, all the way up to the central energy of it. You're seeing about 6 times as many events as when it was there, and ramps back down. Now, the other thing that was important about doing that is remember that our sort of periodic table of the standard model particles had 3 generations, 3 columns. The electron, muon, and the tau neutrino. The up and down quarks, charmed and strange, top and bottom. So the question was were there more? And that's actually something that the calculations go beyond what I can draw pictures of at the moment. But if there had been only 2 generations, the peak would look like this. And if there were 4 generations, that is, that we had more quarks to discover at this point, it would have looked like this. And instead, it's sitting right here. And so, this was strong confirmation that we shouldn't expect any more copies of beyond what we already know about. And in some sense, that's kind of disappointing, but. Now, this, of course, also led to a Nobel Prize. Carlo Rubbia, who at that time was a professor of Harvard, and later went on to be the director general at CERN, put together UA1. And Simon Vandermeer is the one who figured out how you could create antiprotons, collect them, cool them down, store them, put them into a ring in large enough industrial quantities to be able to make this whole thing work. Now, just very quickly, you can have a Z go to a quark-antiquark pair. It can throw off a gluon, like we talked about earlier. In that case, you have quark, gluon, antiquark. You should expect 3 jets. And lo and behold, this is from the electron-positron collider. Electron coming in, positron coming in. You see jet, jet, jet. So each of these, you see the energy being deposited in the hadron calorimeter so that you know that these are jets of strongly interacting particles. And so this was the discovery of the gluon. Same thing with Z goes to, they ramped it up to where you could create pairs of W's. The W's can decay, for example, into quark-antiquark pairs. In that case, you would see 4 jets. And this was the first discovery of a creation. Electron-positron goes to quark, or to W, anti-W with 4 jets.
Who supports the CERN program, and what is this information proprietary, or is it shared with everyone? I think of atomic energy before the Manhattan Project.
The answer to the first question is CERN was created as a treaty organization. And their budget is incredibly stable because the contributions are fixed by treaty. To change it, you have to renegotiate the treaty. That's very different from supporting particle physics in the United States, where Congress has to pass new appropriations, or one hopes they pass new appropriations every year. So that's actually enabled them to carry out long-term planning in a way that we really can't. They're also an international organization, so they're actually exempt from a number of regulations that would affect any national agency, which helps a lot. Now, the other part, and I'm actually going to close my talk in terms of openness of it, but particle physics is probably the most collaborative community of scientists that exists. Collaboration like CMS with 2,200 people, 2,500 people, there has to be an incredible degree of openness. The author lists are alphabetical by name of institution, then alphabetical by person, so that there's no fighting over who's first author or who's priority. And great effort is made to get the information into the public domain very quickly. And you saw an example of this. How many of you saw the press release or the press reports last fall about the supposed neutrinos going faster than the speed of light? Okay, so that was an example where this was an experiment that was doing an experiment and discovered something that they just could not understand. It made no sense. Now, they could have sat on it, But instead, what they did was release essentially all the information into the public domain, saying, here's something that we don't understand. I personally think they should have beat on it a little harder before they did that, but in this case, they actually erred in the side of probably greater and earlier dissemination. Now, what's happened since then is other experiments have been able to carry out comparable analysis and found no effect. Neutrinos don't move faster than the speed of light. And the original experiment, as people were breathing down their neck, discovered two problems with it. One was a cable that was not well plugged in. And well, I mean, think of the complexity of these detectors, right? There's a lot of cables there, and you can't get to all of them very easily. And then the other part was there was actually an error in the interpolation algorithm that they used to take basically GPS readings at the surface down below. And so that I think is an example. Now, as a side, I would say there is an issue with data retention because it's all stored electronically. One of the great challenges is the technology changes very quickly. And so that, for example, experiments that were done at Fermilab, say in the mid-90s, like one of the ones I ran then, all wrote our data to magnetic tape. There's no reader in the world now that can read those data tapes. There's some in museums that might be able to be resuscitated, but there doesn't exist a place you can just put it on. And so there are challenges like that, but that's not an issue of being proprietary. I'll come back to the proprietary issue in a big way at the very end of my talk, because I think it's very important.
With all the institutions and people involved, who is the one that actually makes the decision as to which experiment goes when?
Oh, so that's also a really complicated process. So so CERN has an organization called the CERN Council, which each of the members has representatives to, and the US, which is not a member, has an observer to. They set up a series of committees. So for example, with the experiment that I'm involved in, the process was first a group of people got together in the mid-90s and said we wanted to do this experiment and issued an expression of interest. That was then reviewed by relevant committees to indicate whether they thought it was interesting enough to pursue further or not, and it got the nod. So then it was advanced to, and simultaneously discussions have to be held with each of the national funding agencies to see if they're willing to support people from their country to work on it or not, which is one of the key things. That led then to a letter of intent, which there were then referees that were appointed that asked all sorts of questions about that. There were responses to the letter of intent. Then it advanced to the stage of a series of technical design reports to make sure that you can actually build everything the way that you think it can. Meanwhile, again, further conversations with the funding agencies with each of the nations that have scientists involved as to how much money they're going to put into it to make sure that you can actually finance the whole thing. And so the real answer is it's a very, very collaborative process involving oversight by scientists from many countries over literally a span of 2 decades. So there is no one person that finally does it. I would say there's one exception to that I know of, and that's the experiment that I led at Fermilab with B.J. Bjorkane, where we had the idea for it in the first week of July 1992, and we had to install the first week of May 1993, and there's a committee whose approval we needed that only meets in the second week of June. So in that instance, the director approved it on his own recognizance. But it's a rare issue. Part 3. The Higgs boson, spontaneous symmetry breaking, and the origin of mass. This section also is in 3 parts. The first is on symmetry, broken symmetry, and spontaneously broken symmetry. The second is on the question, what is the vacuum? And the third is the search for the Higgs boson. So Glenn was at CERN a couple of weeks ago and brought back a coffee mug for me. Oh, it doesn't show up too well. Maybe it shows up better for you. It's not worth it, I'll skip it. You can't see it there. We're doing a commentary in this part of the talk on the bottom line. So again, to remind you of the Standard Model. I've said several times before that, that there's 3 generations. There's also other, I've pointed out the similarity between the W and the Z except for the mass. If you also look at the W, I mean, it's charged, and the Z is neutral. But in fact, anytime a Z can go to something like a quark-antiquark pair, a W can go to something like an electron-neutrino or a different quark-antiquark pair, so the charge is suitably conserved. So there's a suggestion here that there's sort of an approximate symmetry involving the photon, the Z, and the W boson, and similarly the quarks and leptons. That is, that in some sense, if you replace one with another, it looks more or less, but not quite the same. Now, the first efforts in the 60s of building a model was to basically say, OK, it's approximately right, but we just put in different numbers in the equations to represent the actual values. And it turns out when you do that, the theory is nonsense. You can't calculate a thing. It's not consistent. And whereas what I'm going to describe is actually the most accurate theory ever devised by man. It can make predictions accurate to 1 part in 10 to the 8th, and you can check it experimentally in some cases to 1 part in 10 to the 8th. That's 10 parts in a billion. So how does this work? Oh, incidentally, the Higgs boson. Why is it called the Higgs boson? This is Peter Higgs. He's the person that gets the credit for suggesting what we're going to be talking about and the rest. He's not the only one that did the work, but he's the one that I think first really got the publicity. I show this picture because it's got to be kind of heady to have someone build a machine that's 17 miles in circumference, detectors that are 5 stories high, spend billions of dollars all to look for a particle named after you. So it's conventional when giving talks at this stage to introduce what's called the Mexican hat potential and symmetry. I decided rather than do that, I would actually bring a Mexican hat. So the point is this is rotationally symmetric. Suppose this direction in some sense were Z, and this were photon in some world, then if you rotated it, it'd still more or less look the same, right? And so there's a rotational symmetry. Now, what we're going to do is talk about how that can be broken, and rather than try and demonstrate it as large as this is, I actually, through the wonders of the iPhone and the ability to take photos quickly, thought I would show you. So in this image, you see the hat. We're looking at it from above. And the grapefruit here represents sort of the state of the Higgs field. And so you can have a situation where it's symmetric. If I rotate it, and again, think of one direction sort of loosely being Z and the other being photon. This state, if I rotate it, it looks the same. The laws of physics wouldn't care how you did it. On the other hand, you can have a state of broken symmetry. If the Higgs boson lives here, that direction's different than the other direction. And so, if you have a mechanism for picking out one, it turns out you can couple it to particles and give rise to mass and everything else and distinguish. Even if the fundamental laws are symmetric, the actual realization of it in the lowest energy state can be different, can be asymmetric. Now, I told you if you just put this in by hand, it doesn't work. But if you do it dynamically, so imagine, you create the universe and you have the Higgs field being at the center. Well, it doesn't want to live there, right? Because the potential wants to roll down the hill of the hat, and it does. And so with the iPhone, I actually waited till it fell and managed to get a series of photos and took those. And so that's a situation of spontaneously broken symmetry. It's something where, it's not something you put in by hand. The dynamics come out. It landed here, it could have landed here, it could have landed there. All of them are equivalent, but each of these would pick out a different direction, which would get mass. So it would be a different combination of the original photon and Z that got mass. So this trick, right, it's kind of a sleight of hand, and was treated in such a way. So much so that when the original model was, for the standard model was written down in the late 60s by Weinberg and Salam, they didn't have any faith that it was any more consistent than the hand version. And in fact, no one referenced Weinberg's paper for the first 3 years after he wrote it. And then a young guy named Gerard de Tooft came along as a graduate student and showed that, in fact, it was all sensible quantum mechanically if you did it this way. Weinberg and Salam picked up Nobel Prizes for it, and Tufte later picked up a Nobel Prize for his contribution. And so, this quirky idea of spontaneous symmetry breaking, in fact, turns out to be the key to making everything work, and indeed is the origin for mass. So how does that work? So, if you're like me, before I got infected with quantum field theory, I thought of the vacuum as a state with nothing in it, just empty space. But that's not the way that once we turn on quantum mechanics we think about it. The vacuum is a very busy place with particles and antiparticles, popping out and annihilating all the time. What spontaneous symmetry breaking does, and what the idea there is to say at each point in space, you've got a Higgs field that can take some value. And if the value of the Higgs field was 0, if it were at the top of the hat, the universe would be symmetric. But there's a potential associated with it, and so it wants to roll down that potential and pick one of the directions that it corresponds to. And so that's happened early in the universe, and picked out a direction. And so all of space is filled with this condensate of Higgs particles. We don't see them directly, but as electrons or W's or quarks go tootling along, they feel the Higgs field, they bounce off it back and forth, and that's actually what gives rise to the mass for those particles. And so, in some sense, it's kind of ironic here at Case Western Reserve. We abolished the ether in the late 1800s, but it's come back through the back door in a relativistically consistent fashion through the mechanism of spontaneous symmetry breaking. So, one of the things is, just as the Cheshire cat, as he's disappearing, leaves his grin. This doesn't just give masses to the particles and break the symmetry. The story doesn't end there. It leaves with a prediction of one more particle that wasn't on the table that I showed earlier, and that's what we call the Higgs boson. It's not a lepton, it's not a quark, it's not a gauge boson. Its mass is unknown. Or at least from the point of view of theory, you can't predict what it is. It couples to all the known particles with strength proportional to the mass of those particles, because it's what gives rise to that mass. So we know how it couples to everything, we just don't know how heavy it is. So much of the work of the last 20 years has effectively been looking for it. And at this point, there's only a very narrow window that hasn't been ruled out. And actually turns out to be the window where it's absolutely the hardest experimentally to look for. When I was first getting into this business 20 years ago, 1989, you knew it was heavier than 10 times the mass of the proton and lighter than 1,000 times the mass of the proton, and that's all we knew. But the hardest range is to find experimentally, just because of issues of backgrounds and ways you can look for it, is between about 120 times the mass of the proton and 130 times the mass of the proton. And it looks like it's right smack in the middle of that range. So, if it's in that range, how do you find it? Well, we're colliding at CERN, protons on protons. Now, at the kind of energies you have there, quarks don't actually matter very much. At those kind of energies, remember I told you that the quarks can spit off gluons, and gluons can in fact spit off more gluons. When you're looking at those kinds of energies, the proton is mostly composed of gluons. The quarks are sort of a perturbation to it. So what the LHC really is a gluon-gluon collider. And the rest of the stuff is just along for the ride. Now, gluons are massless, so the Higgs can't couple to them directly. But the gluons can couple to the top quark, which is the heaviest of the quarks. And so you could have a gluon from one of the beams give rise to a top-anti-top pair. One of the tops bounce off a gluon from the other one, and then the top from one and the anti-top that you created from the other could annihilate, leading to a Higgs boson, which then can decay the same way, but rather than giving off gluons, gives off photons. So one of the easiest channels to see in this range is basically 2 photons coming out, and then just the remnants of the rest of the protons going down the beam pipe. Now, it doesn't have to be top. Any heavy particle that couples to it would do. You could also have the Higgs decay into a W plus W minus pair. And again, you've got this loop of W's. And then since the W's are charged, they can also give rise to photons. So what the experiments are looking for at the moment are events in which they collide proton on proton and see two gamma rays coming out, two photons coming out, and not much else in the event. And where the energy of the two photons adds up to the energy of the Higgs in a very well-defined bump. So this is one of the candidate events that's been announced. So you've got proton coming in here, proton coming in here. The yellow is remember the inner tracking chambers with all the fine detail of ability to track charged particles. So this is all those little mesons coming out from the remnants of the proton. They don't have very much energy. They don't go very far. You know, it's basically uninteresting junk. You see no tracks, and then energy deposited in the electromagnetic calorimeter sort of back to back, and then nothing out further. This basically just shows how it would traverse, so that if there were anything out in the hadron calorimeter or in the muon chambers, you'd know that it was associated with that. So what you see here is a photon, very high energy photon going in this direction, very high energy photon going in this direction, and in this case, the energy of the two adds up to 125 GeV. So this is one of the events that they've identified as a candidate for the decay of a Higgs boson to two photons. Where are we at the moment? So about a month ago, CERN issued a press release. And basically, the bottom line is one of the experiments has basically said it has to be between 116 and 131, the other one between 115 and 227, or 127. If you combine the two, basically both experiments are seeing events of the sort that we just saw in the regime between about 125 GeV, plus or minus 1. There's not quite enough data yet to say that it couldn't at a few percent probability level just be a statistical fluctuation, but it is tantalizingly close. So the expectation is our standard model Higgs analysis with data collected so far leaves us in a very exciting position for 2012. With the data we collect this year, the machine just started running again last week, we will definitely be able to confirm or rule out a standard model Higgs. So a year from now, the expectation is it'll be either thumbs up or thumbs down, and I know which way I'm betting. So now, and so this is sort of the punchline, namely, we're on the verge of finishing off all of standard particle physics. That wasn't an entirely satisfactory point to end the talk. So the question about proprietary nature of the data, anticipating that, I'm often asked, what good is it? There's an enormous amount of effort going into this, an enormous amount of money going into it. And there's a couple of answers. One is that we never know. Maxwell, when he wrote down the equations of electromagnetism in the 1860s, it was decades before that bore fruit in the form of radio. The work on quantum mechanics in the 20s, again, it was decades before the birth of the transistor. And yet, of course, all of our modern society depends on those fundamental innovations. So the real answer is we won't know whether or not something from this fundamental physics is going to be a building block for civilization, really for a couple of decades. However, in the course of putting together this immense project and making it work, there's been one major practical implication. In order for people to collaborate, CERN invented the World Wide Web. And what you see here is the first web server, specifically for the Large Hadron Collider. And then in the spring of 1993, they basically released it to the world, claiming no rights, no royalties, or anything whatsoever. And as you know, it has changed our lives. And if nothing else comes out of it, I'd venture to say that alone was worth the entire project. In any case, thank you very, very much. I'm told I have to end.